Okay, this is one of my favorites. I mentioned this in class because I feel like just about every team sport has you running some kind of patterns, whether it is football, whether it's soccer, whether it is volleyball. Baseball even has patterns, though that one's a little bit different because we don't really try to hit or throw to certain spots. But that's probably the one that has the least. But a lot of our sports have those patterns, hockey, for example. And so in this particular problem, we have this series of vectors that are going to go A, B, and then C. And so our football player is going to start here, and then they're going to run this pattern so they finish down here. So this is going to be the finish point. When I ask the question, what is the resultant vector a plus b plus c, if these are bold like this, what I'm saying is I want you to combine those vectors. So you can also see it with arrows. I would like to know from this point, from here down to here, I want to know this vector right there. So I called it a plus b plus c, but it might actually be better to call this vector r. This is the resultant of it. So when I ask for the magnitude of it, I want to know how long that vector is. When I ask for the direction of it, they kind of help us out. We're going to try to figure out what this angle is right here. So we're going to be trying to find theta. So I'm going to try to figure out what r is, what the magnitude of it is, and what theta is. So here's how we want to do it. I can't just take the fact that A, which is 5 meters, and B, which is 15 meters, and C, which is 18 meters. To get the magnitude, I don't just add them together. I can't go 5 plus 15 plus 18 and say, that's 38, I'm done. 38 meters would be wrong for part A. What I need to do is I need to use a little bit of the component method to break up my vectors. So what I'm going to do is I'm going to take vector C here. Because it is not up and down, north and south, if you will, and it's not downfield or east and west, it's kind of diagonal. I need to break it up and figure out, okay, just like I did in the previous problem, how far further downfield do they run? So I'm going to call this CX because it's a horizontal displacement. And then I'm going to call this one CY. I'm going to break it up into its two components. So I want to figure out how much across the field they go. So how much farther downfield, how much across the field they actually travel. And what that should hopefully help me out is it should be able to tell me those little pieces. Now to find CX, just like we were doing before, it's adjacent to this 35 degrees that they gave us. We should be able to use cosine. So the cosine of 35 degrees would equal CX over my hypotenuse of 18. So if I take 18 times the cosine of 35 degrees, I should be able to find CX. CY is going to be something similar, except that it's opposite it, so I would use sine. That now gives me the pieces. So here's what I'm going to do with those pieces. I'm going to look at R here and say, okay, I know A is heading 5 meters up or 5 meters north, but then later CY is coming down south or coming towards the opposite sideline. So I'm going to break up this vector into how far downward towards this sideline they actually go. I'm going to call this one RY. RY here should be equal to CY, because it's in the same direction, minus this A, minus this 5 meters. Why am I subtracting A? Because it's in the opposite direction. So CY or RY here, should be equal, shrink this for a second, it should be equal to CY minus A. That will give me a number for this side of the triangle. Okay? Then I'm going to do the same thing down here. Is they ran B downfield and then they ran CX downfield. So in other words, they ran a total of RX downfield. What is RX? It's going to be equal to B, because that's downfield, plus how far CX they went downfield. I now have a triangle that is made up of these two vectors, and that should allow me to find this hypotenuse. So my hypotenuse here, my r, should be equal to r squared would equal ry squared plus rx squared. So that's just the that's just the Pythagorean theorem. I should be able to kind of plug those in and figure out what r is. That'll find r for me. Then some people look at my triangle here and say, Mr. Hinnon, you didn't actually find theta sitting outside of your triangle. How do you find that then? So here is my suggestion. There are two different suggestions. One, I always like to find angles around my start. So I would argue that you would find this angle over here. I'll call it phi. If I found angle phi up here, then what I know is angle phi and angle theta have to add up to 90 degrees. So phi would be the complement to that. How would I find angle phi? I could use tangent. It would say that the tangent of angle phi would equal my opposite side, Rx, over my adjacent side, which is Ry. Or in other words, the angle phi would equal the inverse tangent of Rx over Ry. That's one way to do it. That'll find phi, and then I have to subtract it from 90 to get theta. The other one that people pointed out in class is if theta is up here and this little dotted line is horizontal, Rx is supposed to be horizontal. They are parallel lines, and therefore phi or theta here should be equivalent to theta over here. In other words, the other part of my triangle. So I could actually use tangent, but I would switch it. Instead of actually using Rx over Ry to find theta, it would be the inverse tangent of Ry, opposite it, over Rx. That's another way to find it directly. I hope that's a little bit of help with number 6.